Started. So Mudit is going to present his thesis proposal, a dissertation proposal, guidance priors to reduce human feedback burden in sequential decision making. So he will make the presentation first, and then you can ask public session questions about the presentation as well as any background things. And then again, there's a closed session where the committee members can ask questions. So Dimitri, Siddharth, and Tony are the members of the committee. And okay, go ahead. Take it.
Thank you, everyone, for being here for my proposal. So I'll just dive right into the topic, which is guidance priors to reduce human feedback burden in sequential decision making. Okay. So AI systems of today are of varied types. There's so many AI systems, from self-driving cars to Atari games that try to handle maybe virtual home environments like AlfWorld, also robotic manipulation kind of domains, text to video generation. So several of these, they're like AI is at a lot of places. And the more interesting ones for this thesis is sequential decision-making agents, specifically agents which have a human in the loop. What it means is human is present as during the learning phase of the agent. They can be imparting their own, ideally they should be imparting their own preference signals. They could be also present for various other reasons depending on how the framework was set up. But ideally what we would want is for them to be involved, for giving their preferences to the system. But generally it's a sequential decision-making agent with human in the loop. So AI systems need humans, and you can categorize it into mainly two parts. First is for human preferences, which is nice of them because humans can provide their preferences on behaviors, on goals to the agent, and the agent can conform to them, conform to these behaviors, and it's a good human-aware AI system. Agents can also be greedy and try to get guidance information from the human in the loop. And guidance information could be information about the domain dynamics, tricks of getting by in the world, or in fact, commonsensical things, which is not necessarily something that the human in the loop has to provide, but either humans can provide, which is something like common sense, or in fact, humans don't even have to be involved. For example, things like domain information or tricks to solve a domain. But still, there are systems that would want humans to be in the loop as a crutch. So specifically, one of the agents would be, let's say, reinforcement learning agents would need humans for several challenges, including alignment with human in the loop. It could also be for guidance, which is important for other reasons like reward sparsity. There is reward misspecification, feature engineering requirement for reward. So all of these also require some kind of information. But the point I'm trying to get across is the human in the loop should not be the one giving these other kinds of signals. Similarly, there are several fields that try to take a look at each of this. For example, there is RLHF and preference-based RL that tries to align the human preferences with the agent. Of course, these are not mutually exclusive, but you also have reward shaping, IRL or inverse RL or interactive ML or interactive RL that tries to address some part of the same problem, but in different ways. Similarly, also planning agents require, like even for explicit tasks, you would want some kind of common sense information or mental models to make sure that the agent can conform to what the human wants. So synthesize behaviors that the human agrees to, right? And there are also other things you could have asked the human, for example, costs or heuristics. That's also a human can provide, right? So generally, like a very quick background, I'm looking for an agent, not necessarily an RL agent, but I'm looking for an agent to find a policy or find a plan that maximizes the agent's utility. We'll talk about how the utility is defined later on, but this is the overall goal. I'll skip the specific details for now, but okay. So regardless of what the other, like what kind of feedback we take, the typical goals of, we want to understand what is, like, why are we even taking any kind of feedback, right? So I would club it into three main reasons why AI systems need any kind of human interaction. First is to expedite learning, right? You want to maybe get richer signals, solve the reward sparsity problems, obtain these tricks that I talk about to make the life of agent easier. And of course, this can help with improving the performance, right? So of course, human is present in the loop. They can come in, stop the agent from making catastrophic mistakes, provide additional expert knowledge. So all of this is definitely there in terms of expediting learning and improving performance. A more interesting use case of the human's time is to align the agent's behavior with the human's preferences, right? Obtain what they want instead of using humans as a teacher for figuring out the domain. So one of the main central to what I'm trying to talk about in this thesis is this multifaceted view of the role of feedbacks in human AI interaction, right? So I club it into three ways. Humans can be providing domain and dynamics information. I'll talk about some examples of these. Humans can also be giving some kind of guidance on commonsensical things that they believe. And they could also talk about individual preferences, right? What they really think they want out of the agent's behavior. For example, nuance preference could be on the right. If you see that there is a Montezuma's Revenge snippet, all the agent is trying to do is hang around in the world, get the key, open doors, and succeed in that level. Some of the preference could be maybe the choice of door that you want to open first, right? The kind of levels that you want to play first. So those are things that are relevant to the human's preference. Similarly, motion of the robot arm is something that maybe the human has preference over, or the goals of the robot arm, right? Now, that first part was using humans' preference, right? But you could also use humans as a crutch. At which point there are issues that I have with rest of the frameworks. For example, things like you should take the shortest route, watch your timing when you're making jumps across the platforms, or you should avoid like very basic obstacles like skull, etc. This can also be provided by the human, but the question is, should the human be giving this information, or human in the loop be giving this information? Similarly, you could provide tricks of the domain. For example, how far is the key from the door? That can be a useful information for the agent. Or the fact that key is required to open a door, or in fact, whether a robotic arm motion is feasible or not. So things like these are more about whether environment permits you to do something or not, rather than whether human wants to do it or not. But again, human in the loop can still be there to provide this information, but the question is, should they be doing it? And this is where I kind of draw this picture that you have guidance information about dynamics and domain. Of course, human in the loop can be there for everything. Humans can also be there. So the guidance information or common sense information doesn't have to be taken by the human in the loop. You could maybe leverage general humans or maybe some kind of crowdsourced data. I'm hinting at maybe some large pre-trained models. For this special case at the bottom, which is domain and dynamics information, you could leverage the world in which the agent is acting anyways, right? So you don't have to always ask the human to provide that kind of information. You could just figure out maybe some ways of leveraging the world itself. World meaning maybe the simulator in which the agent is acting, or the actual real world in which the agent is acting. So unlike some of the previous works, this is what I want from an ideal agent that I would be happy with, is to not use human in the loop for certain kinds of feedback queries, right? So if you really want information about common sense, dynamics, and so on, try to look for alternate sources of substituting user feedback. So instead of wasting their time on these things, just use them, that is human in the loop, for their preferences, right? So, and figuring out their specific preferences is a very challenging problem. So I'm okay with asking human for that part of it, but rest of it can be maybe mitigated through some alternate sources. So this will be the theme of what I'm trying to do, and I'll be looking for ways of how to reduce the human burden or the burden on the human in giving these feedbacks by figuring out some methods that exposes maybe dynamics or domain information useful when learning from their feedback, or maybe some kind of common sense information extracted through maybe LLMs that can be useful for some other downstream task. But all in all, I'm trying to not ask the human in the loop for this information and rather delegate it to alternate sources, which have a much cheaper cost than just asking the human. Okay, so some of the questions to think about while I talk is, what is the source of this prior going to be? So when I say prior, it is actually some kind of background knowledge or a learning signal that is an alternative to the guidance feedback. Not necessarily like a Bayesian prior, but a background knowledge that we can impart as an alternative. So what would be the sources of this prior? How do we automate it is very important, because the thing that we are trying to do is not use the human in the loop's time to figure out what this prior is, right? So you want to maybe do it in an automated way. And of course, exploring priors or background knowledge that we can get maybe for about commonsensical things. So that is something that we'll explore towards the second half of the presentation. So just to summarize on what I'm trying to do is, feedback from the human in the loop can be used for various things. And of course, I try to divide it into two things: about their preference or about some kind of guidance. Using humans for guidance information, by the vocabulary I'm defining guidance, is using them as a crutch. So that is what I'm trying to avoid. And I believe that is the main source of this inflated sample complexity of these tasks, right? And I'll be taking a look at two, not mutually exclusive, but two challenges. For example, challenge for tacit tasks, where the main bottleneck is figuring out this dynamics information, right? For example, in RL, you don't have dynamics, you have to learn it. That's where a lot of budget goes into when you're interacting with the human. For explicit tasks, you may already have some kind of domain information, right? So most of the budget or interaction goes into figuring out some kind of mental model or common sense. So maybe we can try to look at some alternatives of getting it. So the first part is bottleneck to tacit tasks, which is the dynamics and domain information. As I said, much of the feedback interaction goes into getting dynamics information out of the human. So things like whether this is a good trick to solve this particular task or not, which may or may not have anything to do with their actual preference. So just a quick background on RLHF, which is linked to my discussion, is typical, in contrast to typical RL setup, one of the things that is missing here is the rewards. So in an RLHF setup, rewards are in fact defined by the human feedback. So the agent has no notion of what is right or wrong, and the agent is supposed to query the human to understand what exactly is it supposed to do. There are a few ways of getting this feedback. One of the popular ways is binary feedback, where the agent is trying to query the human. Either, let's say, one of the first ways is action feedback, where the agent would ask, hey, this is this action at this state. Do you think this is a good action? Yes or no? Similarly, a more general work is in terms of comparing trajectory or behaviors. So the agent would propose a couple of trajectories or a pair of trajectories or behaviors, and then ask the human, which one do you like? And again, this is a binary decision that the human has to make. So the process unfolds in this way. The agent uses some base policy or some base method to roll out a bunch of trajectories. And again, it could be informed. It could be, you could do several things in trying to make these trajectories as diverse as possible. But the idea is you first collect a bank of trajectories. Then you query the human. You pick two trajectories. You, meaning the agent, would pick a pair of trajectories, query the human, and ask for their feedback, right? Like, which one do you like? Based on this feedback, the agent would collect all of these feedbacks and try to learn a reward model. And finally, once you have this reward model, you treat it as an RL problem and you learn a policy over this reward. And you can keep repeating this loop. So human is in the loop like as an active loop, because you are querying the human every once in a while. So you would collect trajectories, update the reward function, update the policy, and again ask the human and keep doing it for until the human is satisfied. The way to solve the reward learning problem is to view it as a classification problem. So what you're trying to do is come up with a reward mapping of state actions to some real number such that the return or the sum of rewards for trajectory 1 is better than sum of rewards or return for trajectory 2 if the human label said that trajectory 1 is preferred over 2. So you view this as a classification problem where somehow I want to map numbers to states or rewards such that the return is higher for the preferred trajectory. And then you optimize it just like other classification approach. So this is just a simple binary classification that I want to come up with our psi approximation such that the classifier says trajectory 1 return is higher than trajectory 2. So our objective for this part here is to look for a learning signal, which is the prior or a guidance prior, as an alternative to human feedback. And the objective is that this signal should try to maybe talk about domain and dynamics information. Then we want to inject into reward learning and update the policy. But one question is, before we get into those priors, is why would any reasonable prior help, right? So if you look at the hypothesis space of rewards that we can learn, right? So there are multiple ways. So if you see S0, S1, Sn as a trajectory, and the sizes of these circles as the reward assignment to those states, then there are multiple ways in which I can assign reward such that the return is the same. So the preference label or the way I'm explaining the preference labels is still fine. But the number of ways I can do it is possibly infinite. And this is very problematic for several reasons, right? And a prior can, of course, help in two ways. First is it can cut down on this hypothesis space. So this is more of a practical thing that prior can help with. So we cut down on the hypothesis space, which makes the learning more stable. The other more useful use case is that if the priors are actually of any use, then the thing that I'm cutting down on was not relevant. So I cut down on irrelevant ways of assigning credit. So this is another way. This is like maybe the core reason why a prior should help. So now let's take a look at actually what are these priors that I keep mentioning and what is the operationalization of those priors into this reward learning or policy learning pipeline. So the first thing is, of course, if we need a prior or some kind of background knowledge to support this reward learning setup, then why don't we just ask the human? Of course, it will add some interaction cost to the human, but the point here is we can at least understand whether this prior is of any use or not. Right? If it is not useful, then rest of the things don't really make sense. So the first thing that we do is humans can point and explain their feedback through state annotation. So suppose the human said, hey, I like the action right on this Montezuma's revenge case. And now my question to the human is, why did you pick action right? What do you like in this state? Why do you want to, can you explain your preference in some way? And the interface we allow them to do it is in terms of these annotation maps or some kind of saliency maps in terms of these bounding boxes. So the human can try to annotate objects or regions that they're interested in, that they feel best explains their preference label that they gave to me. And this is a very useful background information. Of course, I'm not doing this in an automated way. This is, again, human is the one giving me. So it's a little more burden on them. But the objective here is to actually try to see whether this is of any use in the first place. The way of operationalizing this prior is very straightforward. It's by definition of what we were trying to do. So the annotations actually mean that, hey, these are the relevant regions that I think the agent should focus on, which means that everything else outside of these bounding boxes is irrelevant to some extent. And if that is the case, then we can do minor perturbations to these irrelevant regions, such as shown here, where you would do some kind of Gaussian blurring over the same state, but you don't touch the annotated region. So the red highlights stay the same, everything else goes under some minor perturbation. And once you do that, you have essentially created a good data augmentation technique that you can leverage. The way you leverage that is you take the policy function, and this is also true when you're doing reward learning. You take the function that you're learning, and you make sure that this function's prediction is invariant to these perturbations. So the fact that something changed in an irrelevant region should not impact my decision making, or should not impact the Q value, or should not impact the rewards that I'm trying to predict. And using this essentially is some kind of a regularization that I'm talking about, that you force while training this agent. So you're forcing the agent to make sure that the predictions for the original state stays the same, even with the perturbations phi's or phi i's. Now, interpreting some of the plots, I would just like to say, is usually like some of the plots that you would see, the x-axis is the environment samples, or the number of samples the agent took. And since the human is in the loop in an iterative way, so human effectively is asked every once in a while. So making sure that we get to a higher score earlier on x-axis means that we are taking less number of human feedback, because they are anyways giving feedbacks in an iterative way. So empirically, what we're interested in is two things. First, whether this prior was useful in the first place or not. So having this context, additional context of these annotated regions, was it useful? And the answer is yes, it was much better than other kinds of augmentations that you could have done in terms of data augmentation. And it is much better than even the way that we injected this prior into this whole learning setup through the regularization auxiliary term is also much better than some other baselines. Okay. So I want to get to the observations that we make out of this work, which actually builds for some of the later two works. What we see is human annotations actually have a pattern to it. And the pattern is more like humans track regions of interest over time. So if they have annotated, let's say, the agent, they would kind of track it over different frames, which is redundant. And that's very good, because then we can automate or figure out a way to automate this part of things. The second observation we make is humans are not necessarily annotating every single frame. Not every single frame is important for their preference. They would try to summarize it in their head in some way and then annotate that. So again, this gives us some avenue of automating or getting this kind of a prior in an automated way without asking human in the loop. So I'll talk about the first observation that we make is coming up with some kind of a temporal distance between states to capture this notion of that humans are trying to convey that states are somehow temporally connected. So just revisiting the setup, we have these two trajectories that I would be showing to the human. And then I would be asking them, hey, what do you like? So I am no more asking any additional feedback or annotation from them. It's just a binary feedback. I'll show them these two trajectories from some buffer, and then I'll ask them for their feedback. And the objective is to learn the reward function from these feedbacks, then learn a policy, and then iterate through this cycle. And the thing that we're trying to do here is extract some kind of a temporal information as a prior that we can inject when learning this reward function. Okay, so the idea is, again, very straightforward, that a state closer to a rewarding state is rewarding. So if you look at this picture, of course, just looking at the L2 distance between the agent and the goal might not be as reflective of how the domain is structured. Right? In fact, one of the things that you can say is, if I had some rollouts for this agent, then looking at the temporal distance might be more useful of figuring out how the state space is structured. This is the premise for action distance. And as I said, the first statement, most of the magic lies in the word closer. And what essentially we are trying to say is define closeness as the number of steps you would have to take to go from a state to another state and come back, right? So if you look at this distance, this is giving you some kind of temporal measure of how far apart or close states are. And the idea of operationalizing this kind of a distance measure or using this kind of distance measure in our reward learning is to preserve this action distance measure. So if two states are 3 units apart, they should be 3 units apart in some embedding space of this approximator that I'm learning. So think of RSI as a neural network. Pick any layer, call it an embedding space. Usually these layers are towards the end or penultimate layers, and force that embedding space to follow this action distance measure. So if I embed 2 states in RSI, the distance between the embedded parts of RSI would be, I'm forcing it to be this equal to this action distance. So essentially, I'm making sure that the embedding space of the reward function should look like this, where if S0 and S2 are 2 units apart, then they are 2 units apart even in the embedding space. The way to do it is straightforward. You already have access to a bunch of experience that the agent has collected in prior iterations. So agent was doing some things through various rollouts or various ways, and I've collected a lot of trajectories that I was anyways doing for querying the user. Take the trajectory, sample 2 states from it, and the distance between them, as in the number of steps that you are away, is essentially the action distance or the dynamical distance between the 2 states. And as I said, take an embedding layer, which is the penultimate layer of this neural network that I use, and force this to be equal to this Dij that we are coming up as targets. So you're essentially like reducing the mean squared between this target that we have come up with and the predicted embedding space. Like in the embedding space, how far apart they are, and you use an MSE just to minimize that. So the main benefit of this work is that we improve the sample efficiency or the number of feedback that we had to query to the human without actually asking anything more, right? So it is a zero cost method, at least with respect to the human in the loop. And we also see that preserving this action distance compared to some other distance measures like L2 or L1 between state features, like raw state features, actually preserving this distance is much better than, empirically much better than those other auxiliary tasks. Feel free to ask questions if you have, but okay. So we'll go back to our observations that we were making, right? So the work number 2 was on observation. The first observation we made about temporal relationship between states that we can probably exploit in an automated way. The second that we'll try to do is exploit this idea that if, let's say, think of any kind of text or video or any sequentially generated something, and then say that if you wanted to give a preference on that, whether you like it or not, do you look at each and every token or each and every frame of that input while coming up with your feedback? Or do you try to summarize it in some way or the other and then come up with your feedback based on that summary? That's in several cases, summarizing can be a very useful thing. So what you do is maybe look at this video, try to summarize it in your heads, and then provide a feedback. That is the main assumption and the intuition of this work. It is very possible that providing a feedback is linked to how you summarize as well. But if you simplify things and say, first I'm going to summarize it, then I'm going to come up with some kind of feedback, then maybe we can try to exploit that. And this is similar to the original thing that we were saying, that humans may not actually annotate each and every frame. They might be selective about what they're trying to annotate. So the idea is that if you look at this trajectory again from Montezuma's Revenge, the agent is trying to jump across from the platform to the rope. There are certain key points that are more important than others. For example, while the agent is in the air, there's not so much that we can do anyways, so it's not as important. maybe the point of launch is very important, the point of land is very important, and so on. So if we could magically get this kind of state importance, then we are doing good, right? Then it would be much useful thing. So next task is to look for some proxy way of getting this state importance measurement. The thing that we empirically test and see that it actually helps is next state prediction. So given a history of states, state actions, or a trajectory, if the objective, or if I'm learning a world model, so to say, to predict the next state, which is at the bottom here, if I learn this world model, then I can use explainable AI techniques to figure out feature importance. Essentially, what I'm trying to say is have a world model that takes in a trajectory, gives out the next state, and see what is the importance of each of the state action pairs that were part of the input. And that I can use as credit assignment. So if you look at what was happening, that is the first bullet, is we want to assign the goodness or the badness based on the preference feedback according to the states that are important in some way. So not all states equally contribute towards the preference. And therefore, when we are trying to assign that binary yes or no, or like I like it or I dislike it into these states back, we should take into account the importance of these states. And essentially, the work does something very similar is you take the goodness of the trajectory, which is given by the predicted return. We already have a reward model that we're using to predict. The more reliable thing there is the return. The credit assignment can be unreliable. So that's how the states get rewarded. We are not so sure whether that's the correct assignment, but the net sum of returns might be a more reliable learning signal. Then you redistribute the way you are assigning rewards to states in the fashion or the state importance prior that we learned. So there are two parts to this figure. On the right-hand side, or the blue box, you see that we can come up with the goodness or the net credit of a trajectory, right? So whether the trajectory is good or bad will be given by this G based on the preference feedback. The left-hand side, or the red rectangle, tries to say, how do we split this G into these constituent states? And maybe this is one way of splitting it. Of course, this could be incorrect and this may not work. But again, this is the background knowledge or prior that we are forcing the system to follow. And then you take this G and again split it back according to these priors that we have computed. And the way we compute prior is, again, we look at the attention maps to figure out which state was important in the input trajectory while predicting the next state. So we have this prior or alpha. We use that to split this G back to these rewards. So we get these target rewards. And then we already have our original reward assignment or the predicted reward. And then the objective is just to match these two distributions or match these two predictions, right? So again, we make use of mean squared error and try to minimize the predicted reward and the target reward that we have computed by redistributing the total credit by using this self-attention weights or state importance weights that we have come up with. We find that there are some practical challenges making sure that the world model can be trained along with the main objective, which is training the policy, training the reward. So there were those practical challenges, and we show that this method can reuse the experience data that the agent was anyways collecting, even for training the world model. We significantly reduce the feedback requirement. And doing this is also, this method is also very robust to feedback noise. So let's say a human sometimes said a different feedback because it's binary. So sometimes they said no instead of yes, or they were inconsistent with their feedback assignment. This method is also very robust to those kinds of settings. Okay. So I mostly talked about the bottom part of this pyramid, which is how can we look at dynamics or domain information? How do we get a prior or a guidance prior or some kind of background knowledge that we can get in an automated way without actually asking the human in the loop? So this was this case. And again, the main bottleneck where this is more prominent is in the case of PBRL or preference-based RL, which is the kind of domains or tacit domains I was looking at. But once we move to more explicit tasks, that problem is less of a concern because you already have a domain model. You already have some knowledge about the domain. So the main concern there is that we don't have access to some kind of common sense knowledge for these explicit planning models or explicit planning problems to generate behaviors or synthesize behaviors that align with the human in the loop. And for that, we'll be taking a look at how large language models can be of use or can be unreliable. So some of the domains of interest here would be typical IPC domains or domains that can be described in terms of symbols. This gels well with the kind of input LLMs agree to, which is text. So it's easier for us to also describe it to LLMs and get some output from them. And the kind of domains we'll be taking a look at is things like household domain or like the fetch robot or several variations of navigation domains. So LLMs, of course, need no introduction, and they seem to offer cheap ways of doing a lot of things, maybe unreliable ways of doing it, but at least it is cheap. To some extent, there is some belief that since large language models have been trained on large scale data, maybe they capture some kind of common sense information of what generally humans agree. And extracting those could be a good guidance information that we can either directly use or use it for some downstream tasks, maybe for RL or for other downstream tasks. So, right. So what we want to do is explore LLM's ability to give us this kind of either preference or common sense information that can reduce interaction with human in the loop for any kind of downstream application. So we'll study actually in two buckets. First is we'll try to explore LLM reasoning, whether it exists or not, how reliable it may be. And the second is explore LLM retrieval abilities and again study maybe how reliable it is for getting some kind of information from them. So one of the first things that we'll do is try to see, consistent with what we have been saying, is we are trying to look for some signal, right? And it was usually a binary signal in our case. Given a plan, given a behavior, would the human like it or not? And that's the first question here, that can LLMs detect plans which are usually desirable to humans in the loop? So assume a robot which is performing some kind of an internal dialogue, and it is doing that dialogue with an LLM. That's why it's internal. And now the robot is trying to use LLM as a human proxy to answer some of the questions. So robot would synthesize a plan and would check with the LLM whether that plan would be a desired plan or not, according to some common sense preference categories. Some of these common sense preferences are on behaviors, are things like explicability, legibility, or predictability, which generally people prefer, and things like obfuscatory behavior that people would dislike. So one example of explicability or legibility would be that robot is taking behaviors or generating behaviors that the human agrees to. So to this end, we propose a benchmark or a data set for perceived behavior recognition or a probe benchmark. The point is that we are trying to tell the LLM that here is a plan that I came up with as an agent. Think what the human would think of this robot's behavior. So it's a second order theory of mind question that we're trying to answer, that LLM has to step into the shoes of some human and then try to answer this question, whether this plan is desirable or not. If it can successfully answer, then that's very good, because for everything that I discussed before, we can just replace or put in LLM in the loop and give those binary feedbacks from the LLM. And this, in fact, is called RLAIF, or reinforcement learning from AI feedback. Okay. So the thing that we do is we take the domains that I talked about. 5 of those domains, again, fetch, navigation domains, environment design domains, and several domains. And we take the 4 behavior types I mentioned, which is explicability, predictability, legibility, and obfuscatory behavior, 3 of which we assume that people generally desire, and 1 of which is obfuscatory behavior, we assume that people do not like that. And what we do is we curate a bunch of situations. And these situations would be like a cross product, right? So 5 times 4. Just for each domain, we curate one kind of behavior situation where the agent is trying to come up with a plan. Then we do a user study to first benchmark how the users respond to this question. Like if I ask the human, hey, look at this video of robot moving around, do you think the robot is going to location 2 or location 3? It depends on the kind of question we are asking. We might give a partial plan or a full plan and so on. And then we try to first benchmark what the lay users would say, which is this purple shade here. Now, we again test the same question to GPT-4. And then we pose actually 2 questions. First is like a binary question. So can GPT-4 tell me whether this behavior is of type X or not? Is this plan explicable or not? Is this plan legible or not? And so on. So we get that as an answer. The second question we ask is, given that you have successfully answered Q1, which is the detection of this behavior, why do you think this behavior is explicable? And again, we pose both kinds of questions. First is LLM has to choose between some MCQ answers or MCQ choices. And second is it has to generate some free-form answers. To summarize all of what this first part of this work did is GPT-4 does really well. It can detect whether plans are explicable, legible or not, and so on. It can also give correct explanations or at least select amongst the choices that we provide, at least at par with what humans said. And in fact, the free-form explanations are also very close and actually people agree to it. So the question now is, can LLMs do theory of mind? Are we done? Can we replace the rest of what we talked about before with LLMs since they can do a lot really well? And the answer is no. The reason is there is a difference between LLMs being able to correctly answer those questions and actually performing any kind of reasoning in order to do so. And to test this, we had 3 perturbation tests. The first is test of conviction. So what we try to do is, okay, what do you expect from a reliable human proxy? At least they should be consistent with what they are trying to answer. Maybe they are saying wrong things, but they should at least be consistent, which is the test of conviction. If you repeatedly ask the same question to an LLM, more likely than not, it keeps changing its response. So even if it can be an LLM proxy or human proxy, it is a very unreliable one. The second thing that we test is inconsistent belief test. For example, if you look at this video at the bottom, the video is blurry. If I show this to you as the human, and if I ask you, where do you think the robot is going? Like, even if I tell you, let's say the robot is going to the left and right, but you only have to infer based on the video that you're looking at, you would more likely than not say that you can't really answer this because the video is blurry. So this simple fact is very hard for GPT models to understand, right? So the fact that I put in that, okay, here is the situation, but unfortunately the signal is corrupted or the human cannot eventually see the robot acting. So this is a very important theory of mind task, right? So this is where you are actually forcing the LLM to do any theory of mind, right? Think from the shoes of the human who really cannot see the robot acting, and therefore the answer should be, I can't say anything for. This completely breaks LLM. It just doesn't do well, like at all. Zeros everywhere. The third thing that we try to test is what if there is uninformative context present in the query that we are posing. For instance, the robot that you see has a very tiny sheet of paper attached on its head. And that sheet actually gives away the answer whether the robot is explicable, legible, obfuscatory, and so on. But the problem is that the human cannot read it. So we come back to the same problem as before, that even though there is context present to correctly answer, like to get the factual answer, which is, let's say, the agent is explicable, the LLM should really say that I can't answer this, or the robot is inexplicable based on the behavior, not what is written on this sheet of paper, simply because the human cannot read it. So again, it has to answer from the perspective of the human, and it fails to do so. So these tests actually showcase the inability of LLMs to be a human proxy. Of course, their performance is better than chance, but that is no reason to say that they're actually reasoning. So it is good to understand, even if we want to use LLMs as a human proxy, it is good to understand where are those abilities coming from. Okay. So now we segue to this other problem, right? So we first talked about, can LLMs detect plans of desirable nature or undesirable nature? Can they also generate plans? Right? Can they provide some kind of a plan? Again, if we have some kind of plan, then we can either use that directly or use it as some kind of a guidance signal for some downstream task. So this is the first proposed work that I'm proposing as part of this proposal. We want to test, right, whether LLMs can provide some kind of plan guidance, right, even with the help of human in the loop. So even if the human comes in and is generous enough to try to provide some hints, such as what React-like systems do, is how do you actually want to reason about solving a certain problem? Even if the human is willing to provide that kind of a guidance, can LLMs come up with plans that are actually correct? Because if they are, then we have host of possibility. Right? We could again go back to our arguments of RLAIF and then just replace everything with LLMs. Some of the initial results that we have suggest severe brittleness of LLMs in this regard. So there is already brittleness in the previous work that I talked about, which just checks for that yes/no detection signal. But for plan generation, it's much worse. Right? And this is important to highlight the good parts as well as the limitations of LLMs as a potential proxy to replace or substitute human feedback signals. So this is the first proposed work. Now taking a step back from LLM reasoning, a good use for LLMs is in fact to explore their retrieval abilities. I'm not really forcing them to do reason, which is kind of out of their expertise, but do retrieval, which more or less they are happier or more reliable for. So this is the second proposed work, is can LLM provides me domain abstractions that are according to some user preference. So what I mean by that is, if you look at the diagram on the top right, if I want to map a domain for a vacuum cleaner robot, I could have been saying several things, right? I could have made up abstract methods, such as go to the room, kitchen, maybe go outside, do something else, and so on and so on. Hierarchical task networks or task decomposition schemas, they allow encoding user preferences during domain design in some ways. First is, I can choose to remove feasible ways of doing something just because it is undesirable. So we try to distinguish that even though going outside is feasible, maybe the user doesn't want the agent to do that, in which case they'll just omit that branch of the tree. The second is the abstractions that I come up with. The fact that I'm saying go to the room, go to the kitchen, I could have just said go, like, be in home. That is another feasible abstraction. So long it is always decomposed to possible primitive actions or actual actions the robot can take. So it becomes interesting to see whether LLMs can come up with this kind of an abstraction that aligns with the user in the loop. Because if it does so, it can help us again in many ways. First, in domain design, the human doesn't have to spend their life designing a domain. They can use LLM's retrieval ability to help them out. And second, if this is reliable and possible, then we can use it for any of the downstream tasks that we talked about. You can, RL actually wants these kinds of models, and there are works that Lynn in my lab shows that if you have any kind of model, that can actually be helpful. So this is the second proposed work in trying to tease out domain abstractions that again conform or align with the user in the loop. So in conclusion, I talked about getting feedback from the human in the loop has two actual use cases. First is in terms of guidance signals, and second is in terms of preference signals. When you talk about guidance, we are actually using humans as a crutch, and that is a very wasteful use of actual human in the loop. My argument is if you have a human in the loop and you want to use them for collecting their preferences and try to at least do your best in coming up with alternative sources to substitute human feedback for the guidance information. So beyond this notion of inflated sample complexity, if we try to study why it is inflated, much of it is not because their individual preference is so complex, which can be, but actually it is because you're also collecting in the name of preference feedback, you're also collecting dynamics information, common sense information, and so on. And we looked at how can we get domain and dynamics priors or guidance priors in the case of tacit tasks or robotic manipulation tasks. And we also looked at investigating what kind of information that we can get about commonsensical things for explicit tasks through LLMs. And that is part of what I propose. Okay, so that's all I have. I think kind of sort of summarizes what all I talked about.
Okay. Okay, so there's time for questions from anybody in the audience, including the committee, of course. Are there any questions for the public forum? Someone, what is good?
Yeah, so I'm curious, when you have a world model that's learned by the agent, it seems like you mostly explored like black box world models, like just a transition function. How do things change if you had like a partially symbolic world model that had like predicates, for instance?
Actually, a version of that work exists as a workshop paper that talks about that if you have access to some kind of symbols of the world, and then you force the world model to reason in those symbols, right? At least in some way. I can get into the details maybe, but if you try to force the world model to use those symbols in some way, then actually it is better. The problem is defining those symbols for tacit tasks can be very hard. So that's why I had to resort to things like Montezuma's Revenge or Atari games where there are meaningful symbols that I can come up with. Of course, even for tacit tasks, it may be possible. For example, Lin has relative attributes work where he's trying to come up with more symbols to explain some tacit behaviors.
Right.
And there also you kind of use it. So I think for sure, if you have, I think what you're trying to say is, can we learn a better world model with these symbols in place? And I think the answer is for sure yes. A lot of newer works are anyways trying to.
It also seems like when you have LLMs involved, they kind of provide symbols in some contexts. Like if you have an HTN, like that's symbolic, obviously. So it seems like that seems like a richer avenue for feedback.
It depends on the, I would say it depends on the domain of interest, but generally for the domains I look at, especially in explicit tasks, I would agree that that's the case.
Any other questions? Okay, do any of the committee members want to ask any questions right now? Should we shift to the closed session? Dimitri, do you have any questions in the public forum, or we should shift to the closed session?
I have questions, but it might be better to discuss them in the closed session because there are also recommendations that I have and so on.
Okay. Okay, then I think the public session is concluded right now. You guys get to leave. Also you should stop the recording because the closed session should not be.
Let me see how to stop.
No, just the recording, just stop it. Stop.
Stop.